Welcome back, students. Myself Sreenivasulu. So welcome back to the YouTube channel of Vidyasketra, so the digital platform, and so I'm your maths teacher on this platform. Before proceeding further, so I request you to kindly subscribe the channel so that you can get the updates, and also whatever the doubts, comments, queries you have, you can kindly enter into the comment section. Thank you. So let us continue wherever we stopped in the last video. In the last video, we have discussed about the conditions for common roots. Okay, so now here in this video, I will be talking about location of roots. So that based on the location of roots, there may be problems, and there are problems being given in your JEE main exam, JEE advanced exam, MSET, EPSET, all these exams. Okay, so definitely it's going to help you. Thank you. Right. So very first case is for the quadratic equation ax square plus bx plus c is equal to 0. If this is the quadratic equation, here if the roots are less than some real number, let us say k, right? What should be the condition? So this condition we are going to derive. Now let us see. So let us try to plot the function ax square plus bx plus c. So whatever I am going to draw here, it represents the function ax square plus bx plus c, not the quadratic equation ax square plus bx plus c is equal to 0. Ax square plus bx plus c is equal to 0 is a quadratic equation. Okay, so we are not drawing that equation. We are drawing the function ax square plus bx plus c. That's all. Okay. So now if you draw the function, this is the case for a is greater than 0. Similarly, this is the case for a is less than 0. A may be greater than 0, a may be positive, or a may be negative, you know well, right? So similarly, it is mentioned that if the roots are less than some real number, so roots are less than some real number means here you need to understand, what you need to understand here is the roots, that means the real roots which are distinct may be less than k, or the real root and which are equal may also be less than k. So there is a chance that roots are distinct and real. Also there is a chance that roots are equal and real, right? So this is the case where distinct roots exist, alpha and beta. So here also alpha and beta. Okay, and this is the case where roots are real and equal. So this represents roots are a real and equal case. That means it may be alpha alpha or beta beta here, right? Whatever it is, the roots are less than some constant k. This is the condition we have taken. Roots are less than some constant k. Okay, both alpha and beta are below the constant k, right? So now if you project this onto the function, okay, so this represents your f of k, and this represents your f of k here. Okay, now let us see the conditions, whatever the conditions we can write here. Okay, so let us see the first condition. If you see here, the first condition is you have real roots, distinct roots, you have real roots, equal roots, but you don't have the case of imaginary roots here. right? So that means the discriminant D must be either it can be greater than 0, strictly greater than 0, or it can be less, it can be equal to 0, but it will not be less than 0. Okay, I hope you will note this point. Yeah. So now discriminant is greater than or equal to 0. This is the first condition, very important. Yeah. Second condition, A is positive, f of k is positive, positive into positive will be positive. A is negative, f of k is negative, negative into negative will be positive. So that means A, the product of A and f of k will be positive. That means greater than 0. I hope you got it. Right. Third case. Third condition. Right. So k is greater than alpha and beta. That means the middle point of alpha and beta, somewhere here, let us say this is the middle point. So middle point is represented by alpha plus beta by 2. So here also alpha plus beta by 2. So as you know, alpha plus beta by 2 is given by sum of the roots. Alpha plus beta is minus b by a. Okay, minus b by a by 2, minus b by 2a. So that means the condition is minus b by 2a, the middle point, is less than k. Less than k. This is the condition for the first case. Right. So what is the first case? For the quadratic equation ax square plus bx plus c is equal to 0, the roots are less than some constant k. Okay, I hope you got it. Right. So let us see the second case. So here the second case is for ax square plus bx plus c is equal to 0, the quadratic equation, the roots are greater than, not less than. The roots are greater than some real number k. It is opposite in that sense, right? So let us plot it and then let us try to see the condition. Right. So for a is greater than 0, concave up. This is a is greater than 0, you have concave up f of x. For a is less than 0, you have concave down f of x, right? And here if you see, this is your alpha, this is your alpha, this is your beta, this is your alpha, this is your beta, and now your k is somewhere here, less than alpha and beta. K is less than alpha and beta. That's what it means, right? The roots are greater than some constant k. That means k is less than alpha and beta. K is less than alpha and beta. So here also you have k somewhere here, right? But also let us project k onto the function. If you project k onto the function, here, so this is your f of k. This is your f of k, right? So once again you can see that a is positive, f of k is positive, a is negative, f of k is negative, positive into positive is positive, negative into negative is negative, right? This is fine. The same thing is carried here also, the second condition, right? Also alpha beta are less than k. That means distinct roots, real roots and distinct roots are less than k. That means the other case where a real and equal roots case is also allowed. This is real and equal case, right? So this is also allowed, right? So that means D need not be strictly greater than 0. It can be equal to 0 also, but it cannot be less than 0. Why? Because we are not talking about imaginary roots here. We have existence of roots here, right? So that means D is greater than or equal to 0. This condition is also fine, right? Now, where is the middle point? Middle point is somewhere here. Middle point is somewhere here. Okay, is it above K or below K? Is it above K or below K? Obviously, minus B by 2A is above K, greater than K. So that means the condition here is, it's not minus B by 2A less than K, it is minus B by 2A greater than K. Okay, so the first two cases differ in the third condition, right? So in the first condition, first two conditions, the first two cases, they have the equal, similar conditions. The third condition is different for the first two cases. For the first case, third condition was minus B by 2A is less than K. For the second case, the third condition was minus B by 2A greater than K. In this aspect, they differ. I hope you got it. Now let me write the third case. So the third case says that the constant K, some real constant K is in between the roots of the equation. So if for ax square plus bx plus c, the third case is some real number is between, so real number is K, between alpha and the roots alpha and beta. Real number K is in between alpha and beta, right? So let me draw it so that you will understand. So once again, A may be greater than 0 or A may be less than 0, right? So for A greater than 0, it is concave up. For A less than 0, it is concave down, right? And this is your alpha, this is your beta. Here also, this is your alpha, this is your beta. And here interestingly, K is in between alpha and beta. So this is alpha, this is beta. Somewhere here you may have K, right? Now, the important point you need to note down here is K is in between alpha and beta. So when I say in between, right, that means when I'm talking about something is there in between something, so that means you need to have two objects to keep another object in between them, isn't it? Okay. So when I say in between, K is in between alpha and beta. So that means you must have two roots, two distinct roots. Okay. If you have single root, that condition cannot be satisfied here. Why? Because you cannot keep K constant in between a single root, isn't it? The sentence itself is, there is a controversy in that sentence, right? So there must be two distinct roots. So that means the first condition, you don't have equality here. It is strictly greater than 0. It is strictly greater than 0 here. Okay? You don't have D greater than or equal to 0. You have D strictly greater than 0. I hope you got it. Right. Second case. A is here. So if you project constant K onto the function, this is your f of K. Similarly, if you project constant K onto the function, this is your f of K, right? Here if you see, A is positive, f of K is negative. Positive into negative, the result will be negative. Here f of K is positive, A is negative. Positive into negative, the result will be negative, right? So A into f of K will be negative for this case, right? So this is negative. Okay, I hope you got it. Now we are saying that k is in between alpha and beta, but we are not sure that k is exactly in the middle point of on the middle point of alpha and beta. Nowhere it is mentioned. So that means there is no point in talking about middle point, right? So that's why for this case this condition is not there. Okay, so we have only two conditions: d is greater than 0, strictly greater than 0, and a into f of k is less than 0. So this is the third condition. I hope you got it, right? So let us see the fourth condition. So for the ax square plus bx plus c quadratic equation, the fourth condition says that one of the roots is between two constants k1 and k2. One of the roots, it may be alpha, it may be beta. Okay, so it will be between k1 and k2, right? So let us draw this. A is greater than 0, concave up. Here you have alpha, here you have beta. Okay, so it says that either alpha or beta may be in between k1 and k2. Let us take the first case. Alpha is between k1 and k2. This is k1, this is k2, right? This is for alpha. So it's when it may be like beta may be between k1 and k2 instead of alpha. Okay, so if you take that case as well, then this may be the case. Here beta is here, okay, and you may have k1 and k2 here. And the root, right? So k1 and k2 may be here, or k1 and k2 may be here. That means the left side root may be between k1 and k2, the right side root may be between k1 and k2, right? So either thing is possible, right? Either of these two is possible, right? So now if you project this onto the corresponding f of x, right? This is your f of k1. This is your f of k2. Similarly, if you project this, this is your f of k1. I'm sorry. We may consider here instead. So left side root is between k1 and k2. Similarly, we may consider right side root is between k1 and k2, right? So right side root between k1 and k2. So that means this is the right side root, right? So let us say somewhere you have k1 and k2. Somewhere here you have k1 and k2, right? Now if we project onto f of x, this is f of k1. If you project this onto f of x, this is f of k2, right? And now you have f of k1 positive, f of k2 negative. Here f of k1 negative, f of k2 positive. So this is for a greater than 0. So for two different curves we have single a greater than 0, right? So here the condition that you may consider is f of k1 into f of k2 is negative always. Why? Because they have opposite signs, right? The same thing can be observed for the case of a less than 0. Let us see. This is for a less than 0, concave down. This is another case, right? Now you have root here, you have another root here, you have another root here. So the leftmost root may be in between K1 and K2. Okay, so K1 may be some here, K1 may be here. Similarly, the rightmost root may be between K1 and K2. Either of these two cases may be possible, right? Okay, now if you project this onto the function, this is f of K1, which is negative. This is f of K2, which is positive. Here also, this is f of K1, which is positive. This is f of K2, which is negative, right? So here also, if you see, f of K1 is negative, f of K2 is positive, positive into negative, negative. Once again, in the other case, f of K1 is positive, f of K2 is negative, positive into negative, negative. So the condition is, for this fourth case, the second condition is f of K1 and into f of K2 is less than 0. Okay, and since we don't have clarity about K, right, here also we don't have condition with respect to middle point between alpha and beta. Okay, I hope you understood. Right. So let us take the fifth case. Fifth case says that for this quadratic equation, both the roots are in between K1 and K2. Both the roots are between K1 and K2. This is the fifth case. So let me redraw this. So wherever you get stuck, wherever you have issue with understanding, immediately please comment in the comment section. So once again, for a greater than 0, concave up. For a less than 0, concave down. This is a greater than 0. This is a greater less than 0. Here you have alpha. Here you have beta. Here also you have alpha. Here also you have beta. Right. So now alpha, beta are in between K1 and K2. This is what it is given, isn't it? Right. So let us say somewhere here you have K1. Somewhere here you have K2. So here also K1, K2, right? So if you project this onto the function, this is your f of K1, this is your f of K2, this is your f of K1, this is your f of K2, right? So now if you see, once again you have distinct roots alpha and beta, real and distinct. So d must be greater than 0. Also when they say both the roots are in between K1 and K2, okay? So both the roots means it means that roots are distinct, right? So when they say that roots are distinct, we can't have equality condition here. So d should be strictly greater than 0, right? Now this is f of K1 positive, f of K1 positive, f of K1 into f of K1, K2 greater than 0, f of K2 negative, f of K1 negative, f of K2 negative, f of K1 into f of K2 greater than 0, negative into negative greater than 0, right? So here you have the second condition, f of K1 into f of K2 greater than 0. As a matter of fact, I can rewrite this. You are dealing with single A here, unlike the previous case, right? So A, f of K1 is positive, A is positive, f of K1 is positive. C, A is positive, f of K2 is positive. greater than 0. Here also it holds good. Here also a is negative, f of k1 is negative. Negative into negative, greater than 0. A is negative, f of k2 is negative. Negative into negative, greater than 0. Right? And there is another condition. So you have two roots, distinct roots. They are between k1 and k2. Obviously, there is a chance that the middle point will be in between k1 and k2 as well. Right? So what is the middle point? Minus b by 2a. So minus b by 2a, it will be in the middle of k1 and k2. That means minus b by 2a is greater than k1. Minus b by 2a is less than k2. Okay? So this is the conditions for case 5, where the roots of ax square plus bx plus c is equal to 0. Both the roots are between k1 and k2. Now let us see the last case, which says that the constants k1 and k2 will be in between the roots. Okay? So both the constants, both k1 and k2 are in between alpha and beta, opposite case. Right? So let me plot it. Right. So first case, a is greater than 0, a is less than 0, concave up, concave down. Right. Alpha here, beta here, alpha here, beta here. Both k1, constants k1 and k2 are between alpha and beta. That means the roots alpha and beta contain in between them the constants k1 and k2. So somewhere here you may have k1, somewhere here you may have k2. Right? Once again there is uncertainty with the midpoint. Right? So here also you don't have condition related to midpoint. Right? So here also k1, k2. Right? We don't know where exactly midpoint lies. It may be away also, it may be before also. Right? It depends on the positions of k1 and k2. Right? So that's why we don't have that condition here. Now let us project k1 onto function. So this is f of k1, this is f of k2. If you project this is f of k1, this is f of k2. So a is positive, f of k1 is negative. Positive into negative, negative. A is positive, f of k2 is negative. Positive into negative, negative. A is negative, f of k1 is positive. Positive into negative, negative. A is negative, f of k2 is positive. Positive into negative, negative into positive, negative. Right? So that means the conditions will be, so the first condition is valid, d must be greater than 0. There is no chance of having equal and real root. Okay, roots must be real and distinct. Right? D is greater than 0. This is true for all the cases. Right? So second case is a positive into f of k1 negative will be less than 0. C, a positive, f of k2 negative will be less than 0. Similarly, a negative, f of k1 positive, minus into plus, minus. A negative, f of k2 positive, minus into plus, minus. Right? So these are the conditions you can apply on problems related to the locations, where the locations of the roots are mentioned by means of some interval. Right? So we will be solving some problems in the next class. Thank you. Thanks for joining. So once again I request you, please subscribe the channel if you didn't, and also you please enter your valuable comments in the comment section, and visit our website of Vidyasketra so that you can get some more updates. Thank you. Thanks for joining. Have a great day ahead.